Hi everyone, I'm Whitroy. Today I invited electrical tutor Mark to review apprentice Sarah's motor test paper. First, I will show all the test questions on the screen. You can have a try yourself. Then Mark will go through Sarah's paper. For each question, tutor will explain why the correct answer is right and why the other options are wrong. I hope you enjoy this style of learning. First, let's start this motor test. 3, 2, 1, go. Now let's review this motor test. 3, 2, 1, go.
Hi Sarah, good to see you. I've gone through your results, 60 out of 90, that's a pass, but it also shows a few key areas where you're not fully confident yet.
Yeah, I feel like I kind of know things, but when the questions get a bit tricky, I start second-guessing.
That's exactly what I saw. So today we'll go through the motor section from the beginning, slowly, and really understand each one, not just the answer, but why.
Sounds good.
Alright, question 1. Rotor speed compared to synchronous speed. What did you pick?
I chose that they are the same speed.
Okay, that's one of the most common mistakes. Let's build it clearly. In an induction motor, the stator creates a rotating magnetic field. That field rotates at synchronous speed. Now, for torque to be produced, the rotor must experience that field moving past it.
So the field needs to cut across the rotor conductors?
Exactly. That cutting induces current in the rotor. That current produces torque. Now, if the rotor spins at exactly the same speed as the field,
then nothing is cutting anymore.
correct. No relative motion, no induced current, no torque.
So the motor would basically stop doing useful work.
Yes, that's why rotor speed must be slightly less than synchronous speed. That difference is called slip, and it's essential. Question 2. Why is slip needed?
I picked to reduce current.
Okay, that's not correct, but it's a good opportunity to understand it properly. Slip is needed to produce torque. It creates the relative motion between the rotor and the rotating magnetic field.
So more slip means more interaction?
Yes, more slip increases induced rotor current, which increases torque up to a point.
So slip is linked to load.
Exactly. The motor adjusts slip depending on load demand. The other options are wrong because slip does not exist to reduce current, it does not increase supply frequency, and it does not control voltage. Question 3. Synchronous speed, 4-pole, 50 Hz.
I got 1500 RPM.
Good, that's correct. Just remember that is the speed of the magnetic field, not the rotor under load. Question 4. Load increases, what happens?
I said speed increases.
Alright, let's think physically. If you put more load on a motor, does it suddenly spin faster?
No, that doesn't make sense.
Exactly, it actually slows slightly. That slowing increases slip.
And increased slip gives more torque.
Yes, that's how the motor responds to load. So speed does not increase, slip does not stay constant, and it definitely does not go to zero. Question 5. What determines synchronous speed?
I said frequency and voltage.
Very close, but voltage is not part of it. Synchronous speed depends on frequency and number of poles.
So voltage affects performance, not speed.
Exactly, that's a key separation. Question 6. Star connection during starting.
I chose higher torque.
That's a classic trap. Let's break it down. In star connection, each winding gets lower voltage compared to delta.
So current reduces.
Yes, but torque also reduces because torque depends on voltage.
So it's easier on the supply but weaker starting.
Exactly. That's why higher torque is wrong. Question 7. Star delta starter purpose.
Reduce starting current.
Correct. That one you've got. Question 8. Starting torque and star delta compared to DOL.
I said same.
Not quite. Since voltage is reduced in star, torque is also reduced.
So lower voltage means lower torque.
Yes, that's a key relationship. Question 9. One phase lost during running.
I thought the motor stops.
That's logical, but not always correct. If the motor is already running, it often keeps running, but with serious problems.
Like what?
Torque drops, but current in the remaining phases increases. That causes overheating.
So it's actually worse than stopping?
Exactly. That's why it's dangerous. Question 10. Effects of single phasing.
I picked lower current.
That's the opposite of reality. The motor still tries to produce torque, so the remaining phases carry more current.
So current increases and heating increases.
Yes, that's why it's dangerous. Question 11. Balanced system, neutral current.
0.
Good, that's solid. The three-phase currents cancel each other out. Question 12. Power factor of a motor.
I said unity.
Motors are inductive, so power factor is lagging.
Because of the windings.
Yes, current lags voltage in inductive circuits. It is not leading, not always unity, and it changes with load. Question 13. 3-power calculation.
I forgot power factor.
That's the key mistake. Real power depends on voltage, current, and power factor. For 3-phase, you also include root 3.
So if I leave out power factor, I get the wrong answer.
Exactly. That's one of the most common calculation errors. Right, Sarah, let's pick up from question 14, because from here on, a few of these need a bit more unpacking.
Yeah, I felt from around there I was more guessing than really understanding.
That's honest and that's useful. Let's fix that properly. Question 14. Power factor correction using capacitors connected to a motor will what?
I got that one right, I think. Reduce line current drawn from the supply.
Yes, that is correct. Now let's go a bit deeper because this is one of those questions people often get right for the wrong reason.
Okay.
Right. An inductive motor is an inductive load. That means it needs not only real power to do useful work, but also reactive power to establish its magnetic field.
Right, so some of the current is not doing useful work, but it is still needed.
Exactly. The supply still has to carry that reactive current. Now, when we add capacitors for power factor correction, the capacitors supply some of that reactive power locally, right near the motor.
So the supply does not need to provide as much.
Correct. That means the current coming from the supply reduces. The motor still does the same useful work, but the line current is lower.
So why is increased reactive power demand wrong?
Because capacitors do the opposite. They reduce the reactive power demand seen by the supply. They don't make the motor need more. They help cancel part of the inductive reactive demand.
So reduce motor speed is wrong because power factor correction is not speed control.
Exactly. It does not directly change the motor speed. And increase supply frequency is clearly wrong because capacitors do not change supply frequency. Question 15. Which two are correct effects of improving power factor in a system?
I chose reduced current for same power and reduced losses in cables.
Good. Both are correct. Now let's connect those clearly. If power factor improves, then for the same real power output, the system draws less current.
Because less reactive current is needed from the supply.
Exactly. And once current drops, cable losses drop too, because cable heating losses depend on current squared times resistance.
So even a moderate drop in current can make a noticeable drop in losses.
Yes, that's a very important idea. Now let's look at the wrong options. Increased voltage drop is wrong because voltage drop generally gets better when current reduces.
Since voltage drop is linked to current through the cable resistance.
Correct. And increased reactive power is wrong because improving power factor means reactive demand from the supply is reduced, not increased.
So this question is really about understanding the flow-on effects of lower current.
Exactly right. Question 16. A universal motor is commonly used in portable tools. How is its speed typically controlled?
By varying the supply voltage.
Correct. Now let's make that a bit more solid. Universal motors are common in tools like drills and mixers because they can run at high speed and have good starting torque.
Yeah, I've seen them in hand tools.
Good. Their speed changes a lot with supply voltage and load. So if you vary the applied voltage, you vary the speed.
Why is changing supply frequency only wrong?
Because in the usual practical control of a universal motor, voltage variation is the main method, not frequency control. Frequency-based control is more associated with AC motor drives, especially induction motors with VSDs.
So altering pole number is not the normal setup for a small universal motor.
Correct. And increasing slip is wrong because slip is not the control idea used for a universal motor in that way.
Question 17. A single-phase induction motor is not self-starting because what?
It produces a pulsating magnetic field rather than a rotating field.
Correct. This is a very important concept. In a three-phase motor, the three-phase supply naturally creates a rotating magnetic field. But with plain single-phase supply, the field just grows and shrinks, grows and shrinks.
So it sort of pushes equally both ways?
That's a good way to think of it. It does not naturally create a preferred direction of starting torque. That's why the motor won't self-start unless we add some way to create phase shift and a more rotating effect.
Why is it has no rotor winding wrong?
Because many single-phase induction motors do have a rotor, often a squirrel cage rotor. The problem is not the absence of a rotor, the problem is the type of magnetic field produced by the supply arrangement.
And supply voltage is too low is clearly not the real reason.
Correct. The motor could still fail to self-start even at normal voltage if there is no suitable starting arrangement. And it has no slip is wrong because slip still applies once the motor is running. Question 18. Which two methods are used to start single-phase motors?
Capacitor start and split phase.
Yes, let's explain both. Capacitor start motors use a capacitor in the auxiliary winding to create phase shift. That gives a stronger rotating effect and better starting torque.
So the capacitor helps make it behave more like a rotating field.
Exactly. Split-phase motors also use an auxiliary winding, but the phase shift comes from different winding characteristics, mainly resistance difference rather than a capacitor.
So both are trying to solve the same starting problem.
Yes, that's the key. Now, star delta is wrong because that is a three-phase starting method. Auto transformer is also not the normal answer here for basic single-phase motor starting. Question 19. In a capacitor start motor, the capacitor is used to what?
Create phase difference for starting torque.
Correct. Let's make that very clear. The capacitor shifts the current in the auxiliary winding so that its magnetic field is out of step with the main winding field.
And together they create more of a rotating field.
Yes, enough to develop starting torque in one direction. That's the whole point.
Why is reduced supply voltage wrong?
Because the capacitor is not there as a voltage reducer. Its job is phase shift. Increase frequency is wrong because passive components like that do not change supply frequency. Limit current permanently is wrong because the starting capacitor is about creating starting conditions, not acting as a permanent current limiter. Question 20. In a three-phase system, if phases become unbalanced, which effect is most likely?
Neutral current will increase.
Correct. In a balanced three-phase system, the vector sum of the three-phase currents is zero, so neutral current is zero. But once the loads become unequal, that balance is lost.
So the currents no longer cancel each other out.
Exactly, and that difference shows up as neutral current. That's why the option saying all phase currents remain equal is wrong. If the loads are unequal, the currents are not equal.
And voltage becomes constant is not really answering the actual effect.
Yes, and it is misleading. Frequency changes is also wrong because load unbalance does not change system frequency. Question 21. A three-phase system supplies unequal loads. Which two effects may occur?
Unequal phase currents and neutral current flow.
Correct. These two belong together. Unequal loads mean unequal currents, and because the currents are unequal, they do not cancel in the neutral.
So if I only chose unequal phase currents, I'd only be half right.
Exactly, and that's an important exam lesson. Often one effect leads directly to another effect. Balanced voltage always maintained is too absolute and is not the correct answer here. Zero current in neutral is definitely wrong for unequal loading. Question 22. Phase sequence in a three-phase system determines what?
Direction of motor rotation.
Correct. Think of phase sequence as the order the three phases arrive. That order determines the direction of the rotating magnetic field.
So if the order changes, the field rotates the other way.
Yes, it does not determine voltage magnitude, it does not directly determine current value, and it does not determine frequency. Question 23. If two phases are interchanged in a three-phase motor supply, the motor will what?
Reverse direction of rotation.
Correct. Swapping any two phases reverses the phase sequence. Reversed phase sequence means reversed rotating magnetic field, so the motor turns the other way.
It won't just stop.
No, not normally. If everything else is healthy, it will run in reverse. That's why phase sequence matters so much for pumps, conveyors, and fans. Question 24. Which condition will increase starting current of a motor?
Direct online starting.
Correct. DOL means full supply voltage is applied immediately. That gives the highest inrush current.
So the other starting methods are mainly there to reduce that.
Exactly. Star delta and reduced voltage methods lower starting current. Power factor correction is not a starting method, so it is not the answer. Question 25. A motor is overloaded. What is the primary effect on current?
Current increases above rated value.
Correct. The motor has to produce more torque to carry the extra mechanical load, so it takes more current.
So overload is basically an electrical sign of too much mechanical demand.
That's a very good way to put it. The wrong answer, saying current decreases to maintain speed, is wrong. Current does not magically fall when the motor is struggling. Current remains constant is also wrong, and current becomes zero is obviously wrong. Question 26. Which two conditions indicate motor overload?
Excess current over time and temperature rise in windings.
Yes, that's the key overload pattern. Too much current for too long produces excess heat in the windings.
So heat is really the damage result and current is the cause.
Exactly. That's why overload protection is often thermal in nature. Reduced current flow is wrong and improved efficiency is wrong because overload generally makes operation worse, not better. Question 27. Motor overload protection is designed to respond to what?
Current over time characteristics.
Correct. This is very important. A motor can draw high current for a short time during normal starting, and that may be acceptable. But if elevated current continues too long, that becomes overload.
So the protection needs to consider both how much current and for how long.
Exactly. That's why instantaneous voltage rise only is wrong. Frequency variation is wrong. Short circuit only is wrong because overload and short circuit are not the same thing. Question 28. Which protective device is typically used for motor overload protection?
Thermal overload relay.
Correct. It is designed to follow the heating effect of current. If the motor draws too much current for too long, the relay trips.
Why is RCD wrong?
Because RCD protects against residual current imbalance, mainly for shock and earth leakage situations. It is not there to protect the motor against overload heating. Isolator is just for switching and safe isolation, not automatic overload protection. Fuse only is not the best answer because a fuse is mainly associated with overcurrent and fault protection, not the proper motor overload behavior modeled by thermal devices. Question 29. In a motor circuit, which two functions are provided by a starter?
Control starting current and provide safe starting method.
Correct. A starter is there to help the motor start in a controlled way and often to include useful control and protective functions depending on the design.
So not increasing frequency.
Correct. And not permanently reducing supply voltage. Some starters reduce voltage during starting only, but that is not the same as permanently lowering it.
Question 30. A motor operating at low voltage will typically draw what?
Higher current to maintain torque.
Correct. This is one of the most important trap questions in motors.
Yeah, because it feels like lower voltage should mean lower current.
That's exactly why students get caught. With many loads, lower voltage can mean lower current, but with a loaded motor trying to keep producing torque, the motor often draws more current when voltage drops.
So lower voltage can actually create overheating risk.
Yes, torque capability drops, current rises, heating rises. The option saying lower current is wrong in this context. No current change is wrong, zero current is clearly wrong.
Yeah, this part definitely needed more detail.
It did. From question 14 onward, a lot of them are system behavior questions. If you only memorize a sentence, you can still get tricked.
I can see that. It's more like one thing causes another thing.
Exactly. Capacitors change reactive demand, unbalance causes neutral current, low voltage affects torque and current, overload affects heat, and phase sequence affects rotation. It's all connected.
That helps a lot more than just hearing the answer.
Good. That's what revision should do.